Hi everyone, Ross Satchell from Microchip back again. Welcome to episode 10 in our AVR bare metal series. In the previous video, episode 9, we moved the USART0 transmit driver code that we developed in episode 8 into separate header and source files. This is so that we can simply include that library into a project and don't have to write every new project from scratch every time. We can just include the library for a peripheral and use it as a building block. Also, by using the human-readable macros in our library driver, if a compiler change happens with a new version, we can simply update our driver to use the new human-readable macro, meaning that maintaining our libraries is much easier and far less error-prone. In this episode and the next 2 episodes, we will set up the ADC peripheral to read an analog pin, check whether it's within a user-defined window, and print both the ADC result and whether it satisfies the window condition to the terminal using the USART TX driver that we created in episode 8 and turned into a USART library in episode 9. Then we will rapidly accumulate 16 samples using the ADC peripheral. This is much faster than taking multiple samples in software and is very useful when taking analog readings in noisy environments, as by accumulating samples rapidly, we can cancel out random noise. We will use this extra sampling to increase the effective resolution of the ADC from 12-bit to 14-bit using a process known as oversampling and decimation, which we will cover in these ADC episodes. We will also use the window detection feature to determine whether the oversampled and decimated ADC result is within a particular range that we will specify. I will also go over how I broke the clock control function out into a library with header and source files. So let's get started. Open the project from episode 9 and make a copy of it, just like we did in the last video. I will change the name of the copy to episode 10-A, since we will be extending last episode's code for this episode, and we will be breaking the ADC peripheral over 3 episodes. First, I will quickly show you the library I made for the clock control peripheral, as some of the concepts used there will also be used in these ADC episodes. In the header file for the main clock control, we can see there are 5 parameters passed to the function and it has a void return. I have some comments there explaining the parameters. So first is clock select, next is frequency select, then prescaler enable, prescaler divider, and finally clock out. All parameters except for prescaler enable and clock out use enum data types, which we covered in the previous episode. Prescaler enable and clock out both use an unsigned 8-bit integer data type. We could have also used a char, that is character, or we could have used a boolean, which requires us to include the library standard bool. It is worth noting that using the standard bool library would increase our code size by 2 bytes overall. The main point here is that they will all work. Then if we jump to the main clock control source file, we have the function implementation. You may have already noticed that some parameters depend on other clock control parameters. What I mean by that is if the user selects the 32 kHz internal oscillator in clock select, then whatever is written to the frequency select will not be used, since that is for the high frequency oscillator only. So if the user disables the prescaler enable, then whatever is written to the prescaler divider will not be used. So I have a protected write for the main clock control A register that writes the clock selection bit shifted to the left using the macro clock control underscore clock select underscore GP, which is then bitwise ORed with clock out bit shifted to the left using the macro clock control underscore clock out underscore BP. Let's control and click to follow the clock out macro and also open the datasheet to the clock control register summary. You may recall from episode 2 we talked about bit masks and touched on bit positions. However, we haven't actually used bit position macros yet in this series. To start with, it's important to know that masks for bit positions are suffixed with underscore BP. In the header file, we can see the system clock out bit position is 7. Then looking at the datasheet clock control register summary, in the main clock control A register, we can also see that clock out is located at bit position 7. So the macro ending in _BP is the bit position in the register where that particular bit resides. So when calling the main clock control function, if the user writes a 1 for the clock out parameter, then that gets shifted over to bit position 7. Similarly, if a user writes a 0 for the clock out parameter, that also gets shifted over to bit position 7. Now, as a quick tangent, you might be wondering what happens with a multi-bit register setting such as clock select in main clock control A register. Looking at the main clock control A register in the datasheet, we can see that the least significant bit is at bit 0 and the most significant bit is at bit 3, with the setting covering 4 bits. Now if we go to the header file in MPLABX that we opened earlier when we followed the clock out bit position macro, just above that macro are the macros for clock select. The one we are interested in is the one ending in _GP, as it's the group position. So the code is actually bit shifting the clock select parameter to the left 0 times. This is a bit redundant, but it is good practice to avoid making simple errors when writing drivers. So returning to our main clock control C source file, where we were writing to the clock out bit in main clock control A register, if the user writes a 0 to that function parameter, meaning they do not want to use the clock out functionality, we can use the clock control _clock out bit position macro to write a 0 to that bit. What that means is we don't have to use a NAND in the form of the current register setting, bitwise ANDed with the inverse or bitwise NOT of the register bit of interest. I'm not saying one is better than the other, just that the user can decide on whichever one they prefer and feel more comfortable with. Next, in the main clock control function, there's an if statement for the function parameter prescaler enable, where if the user has written a 1 to that function parameter, meaning they do want to use a prescaler, then the prescaler divider parameter as well as the prescaler enable will be written to the main clock control B register. However, if the prescaler enable is 0, then only that prescaler enable will be written to, since it's not using a prescaler divider. Next is if the high frequency internal oscillator, OSC-HF, is used, then the supplied parameter for frequency select is also used. Finally, if the clock out parameter is 1, then the clock out pin, which on the AVR DD Curiosity Nano is pin PA7, is set as an output. The main takeaway here is the use of bit position masks and group position masks. For more detail on that, you can take a look at section 3.3 of the tech brief TB3262, Getting Started with Writing C Code for AVR MCUs, linked in the description below. Before we write our ADC driver, I will set up the hardware. I have a 10K ohm potentiometer and have connected one side to VDD, the other side to ground, and the wiper is connected to pin PF2. So now let's start on our ADC library. Open your datasheet to section 33, ADC. In the overview, it mentions that the ADC used is a successive approximation register, or SAR. These are often found in applications requiring medium to high resolution. SAR basically uses a binary search algorithm to digitize the continuous analog input signal. The details of that are outside of the scope of this video, but you can search YouTube for videos on how SAR ADCs work. The ADC has a sampling rate of up to 130 kilosamples per second, that is, 130,000 samples per second, when running at 12-bit resolution. It has an internal multiplexer that allows for selecting single-ended or differential inputs. Single-ended conversions measure the voltage on a given pin with respect to ground or VSS, while the differential conversion measures the voltage difference between two selected input pins. The ADC input signal is fed through a sample and hold circuit, which keeps the input voltage to the ADC stable while being sampled. Sampling in bursts is supported, and users can set the number of samples that are accumulated into a single ADC result. Also, a sampling delay can be configured, which allows the user to tune the ADC sampling rate away from any harmonic noise, for example, mains power frequency. The ADC uses a configurable voltage reference for the maximum value in the ADC range, and this is set using the VREF peripheral, where users can leverage one of the multiple internally generated voltage references, a VDD, which is the supply voltage, or an external voltage reference. Let's take a look at the block diagram. We can see in the center the ADC peripheral itself, which uses a reference voltage. We can also see the positive and negative multiplexers for the inputs. On the right is the accumulator, the result of which can be formatted using the control logic. Then there's the ADC Result Ready register with a Result Ready interrupt, or IRQ, and also a window compare interrupt. In the table under Signal Description, there's only two signals, being analog inputs to be converted and external voltage reference pin. Under the functional description, we first have some definitions. Conversion is the operation in which analog values on the ADC inputs are converted into a digital representation. Sample is the output of a single ADC conversion. Result is the value that is placed in the ADC result register, and this can be a single sample or an accumulation of multiple samples. Under that is an initialization procedure for taking basic measurements. We will be building a more complex ADC driver, but still it's good to have some familiarity with the basic setup. So let's go through it. 1. Configure the ADC voltage reference in the VREF peripheral. 2. Optional. Select between single-ended, that is, an ADC read with respect to ground or VSS, and differential mode, which is set by the conversion mode bit in the Control A register. 3. Configure the resolution using the resolution select bit field in the Control A register. 4. Optional. If required, configure left adjust of the ADC result using the left adjust bit in the Control A register. 5. Optional. Select free running mode by writing to the free run bit in the Control A register. 6. Optional. Configure the number of samples accumulated in each ADC conversion by writing to the samp num bit field in the Control B register. 7. Configure the ADC clock by writing to the prescaler bit field in the Control C register. 8. Select the positive ADC input using the MUX-POS bit field in the ADC MUX-POS register. 9. Optional. Select the negative ADC input using the MUX-NEG bit field in the ADC MUX-NEG register. 10. Optional. Enable start event input by writing to the start event enable bit in the EV control register and configure the event system accordingly. 11. Enable the ADC by writing to the enable bit. Once the ADC peripheral is initialized and the enable bit set, but before a read can be performed, the ADC needs a warm-up time before reliable results can be returned. This delay can be manually implemented in code, or you can use the initialization delay bit field in the Control D register. If using the init delay bit field, it needs to be set to a value that is greater than or equal to the product of the ADC warm-up time and the ADC clock. It mentions to see the electrical characteristics section of the datasheet for more information. So let's quickly check that out. Section 38 is electrical characteristics. Then under that is ADC, so let's click that. There's a table with accuracy specs, then after that there's a table with ADC conversion timing specs. That's what we want. The last row is initialization time, and it is 6 microseconds, but there's a note that data in the typical column is for an ambient temperature of 25 degrees Celsius and a VDD of 3 volts. Since we're using a Curiosity Nano dev board, The default VDD is 3.3 volts, so we can reasonably expect a fairly similar initialization time. Now back to the ADC section. To start a conversion after the initialization time has elapsed, the conversion can be started by writing a 1 to the start conversion bit in the command register. This bit will remain a 1 while the conversion is in progress and will be cleared once the conversion is complete. Depending on the accumulator setting, a conversion can be a single sample or from 2 up to 128 accumulated samples. Once the triggered ADC read operation is complete, the res ready flag in the int flags register is set. If using an interrupt, the interrupt vector will be executed if both the res ready interrupt enable bit in the int control register is set and the global interrupt enable bit is also set. Note that even if the global interrupt enable is not set, the res ready flag in the int flags register will still be set when the ADC result is ready. This means that we can check it in software by polling that bit after starting a conversion. So a conversion can be triggered without causing an interrupt when it is completed. Further down is clock generation, where the minimum ADC clock frequency is 125 kHz. There is an ADC prescaler from the peripheral clock to generate the ADC clock. Now you may have noticed in some of the episodes in this series, we have used the 32.768 kHz ultra-low power internal oscillator, but the minimum ADC clock frequency is 125 kHz. This means that if we're using the ultra-low power internal oscillator, then we will need to switch to a clock that meets or exceeds this 125 kHz requirement. We can see in figure 33.3 that the ADC prescaler options range from the peripheral clock divided by 2 to the peripheral clock divided by 256. Since the smallest prescaler is 2, that means we need a peripheral clock that is at least twice the 125 kHz minimum for the ADC, that is, a 250 kHz minimum peripheral clock. If part of your project was low power and you needed to do ADC reads, you could use the 32.768 kHz internal oscillator for most of your code and then temporarily switch to a faster clock for the parts requiring that. Next is conversion timing, that shows us that a single ADC conversion starts with the user writing a 1 to the start conversion bit in the ADC command register. If we follow along with figure 33.4, the ADC then starts up for a maximum of 2 peripheral clock cycles. It then does sample and hold for 2 ADC clock cycles. Next, it performs the ADC conversion for 13.5 ADC clock cycles. And finally, it formats the result for 2 peripheral clock cycles, which is shown in the diagram as AFV. The time for a single conversion is shown as an equation just below the figure. We can see it's broken into 2 parts, since the time taken is dependent on both the ADC clock and peripheral clock. In an upcoming video, we will also do accumulated conversion, which is just below that in the datasheet. We can see the same 2 peripheral clock cycles for startup, and it samples for 2 ADC clock cycles, converts for 13.5 ADC clock cycles, then formats for 2 peripheral clock cycles. Then it samples, converts, and formats over and over until it reaches the required number of samples. The equation below reflects this. We can see the startup time, then the sample and hold along with the conversion, and then finally the formatting. Those are multiplied by n, where n is the number of samples accumulated. We will not be doing a free-running conversion in this example. The next part is about adjusting the conversion time. The conversion time can be adjusted with 2 parameters, being the sampling length and the sampling delay. Adjusting the sampling length allows for sampling analog inputs with high impedance sources. In this case, the user would need to calculate the total input impedance to determine how long it would take for the sampling capacitor to fully charge and make sure that the time they use for the sampling length meets or exceeds that time. The advantage of using this is that the user does not need to reduce the ADC clock frequency. Adjusting the sampling delay allows the user to tune the sampling frequency away from any harmonic noise in the analog signal. This now gives us two new equations. The first is for the sample time, and the second is for the total conversion time. Figure 33.7 gives us a visual representation of the use of sampling delay and sample length. Next, we have conversion result. A single-ended 12-bit conversion result is the analog voltage divided by the voltage of the ADC reference multiplied by 4096, which is 2 raised to the power of 12, that is, 12 bits, where the result is an element of the integer set ranging from 0 to 4095. Similarly, a single-ended 10-bit conversion is the analog voltage divided by the voltage of the ADC reference multiplied by 1024, that is, 2 raised to the power of 10, that is 10 bits, where the result is an element of the integer set ranging from 0 to 1023. Conversions are stored as right adjusted by default. However, the ADC result can also be left adjusted if required. When accumulating more than 16 samples, in order to avoid overflowing the result register, the least significant bits are truncated to fit within the register. Table 33.1 shows this with a single conversion taking up a total of 12 bits, then 2 accumulated samples take up 13 bits, 4 accumulated samples take up 14 bits, 8 accumulated samples take up 15 bits, and 16 accumulated samples take up 16 bits. Beyond that, the accumulation is truncated. Next is channel selection. The user can select both the positive and negative inputs using the mux-pos and mux-neg registers respectively. If operating in single-ended mode, then only mux-pos is used. Once the conversion starts, the channel selections are locked to ensure sufficient sampling time for the ADC. Updating of channel selection resumes in the last ADC clock cycle before the conversion is complete, with the next conversion starting on the following rising edge of the ADC clock after the start conversion bit is set to 1. The ADC also includes an on-chip temperature sensor, which is used with the internal 2.048 volt reference. The ADC has a window comparator function which will raise the window compare interrupt flag in the ADC int flags register and request an interrupt if the result of either a conversion or accumulation is above and or below certain thresholds. The available modes are when the ADC result is either above or below a threshold, as well as inside or outside a specified window. These thresholds are user-defined and are written to the window comparator low and high threshold registers. To reduce power consumption, users can disable the digital input buffer pins that are used for the ADC. This is the same as we did in episode 6 of this series. The ADC can be used to generate and use events, although that is outside of the scope of this episode. There are 2 available interrupts, being the ADC Result Ready interrupt and the ADC Window Compare interrupt. Note that it says when an interrupt condition occurs, the corresponding interrupt flag is set in the int flags register. An interrupt source is enabled or disabled by writing to the relevant bit in the int control register. An interrupt request or IRQ is generated when both the interrupt source is enabled and the interrupt flag is set. However, we will just be using the interrupt flag in this example without generating an interrupt request. By default, the ADC is disabled in standby sleep mode, but can remain fully operational if the run standby bit is set in the control A register. We will not be using sleep in this episode. To keep these episodes at a reasonable length, we will write the ADC initialization function in the next episode. See you then.